between in air and in water. So there's this n squared correction that you have for that. So there's an immersion factor in the checkoff boxes for the radiance detectors that you're going to be playing with during the radiometry lab. Okay, other problems. The light level changes between the field and the lab, so you have to worry about the linearity of your detector. As I showed you, the lamp is completely different colored than anything you're going to see in the field, so you have to worry about that. Worry about temperature variations, you've heard about that. Scattered light in the lab, geometric setup in the lab, drifts in your calibration sources. There's all sorts of things you have to be careful if you're going to try to do the calibration yourself. Most labs are probably not set up to do that well enough. What you'd really like to have is some source you could look at that's stable, that you get the calibration back from the manufacturer, and in your lab you're using that as a stability check as you're going along. For the most part, that's probably the best thing you could do. Now, that was all in-water radiometry things. Since this is, like I said, a satellite class, what the satellite measures is the radiance coming up from the surface, and we'd like to come up with some factor that is related to that radiance that's less dependent on the illumination conditions. So what people have been using lately is the remote sensing reflectance, LW over ES. And LW is the water-leaving radiance from just above the surface, and ES is the downwelling irradiance. Okay, so real simple factor. The above-water techniques, there's, I'm not sure, I want to get this because we're going to do some of this in the lab. The above-water techniques is you measure the light coming up from you, at you, above the surface, the radiance, and divided by the irradiance coming down. The radiance, LW, the water-leaving radiance, you have to, when you're measuring it above the surface, you've got to take account the surface itself. And so you have to take the radiance you measure and subtract off the glitter from the surface, which is the radiance from the sky times the reflectivity of the surface. So you can see I'm making a measurement down, looking down like this with my detector at the surface. Some of it's going to be light that comes up. And so this is LW. Well, this is LW minus. What you look at above the surface is LW plus. But some of the light also is skylight that's come down to the surface and bounced up. And so the total signal you measure here will be LW plus, plus some sky times some reflectance factor. So to measure, what you really want is just LW plus, and so you have to subtract off this. And Kurt's the expert at making calculations of that. And so here's one paper he's got. He's got a newer paper. Is it published now? Yeah. Okay, so a newer paper describing this, including polarization effects from the surface.
When you get to the lab, they're on the Oceanoptics website under remote sensing level 3 or something. You can download this file that says, you know, if I'm looking at 40 degrees off the nadir and 135 degrees from the sun and the wind speed's 5 meters per second, here's the fudge factor you need for this row or whatever Ken called it. And there's the old 1995 file, and then there's a newer file that's recomputed accounting for polarization for clear sky days. So use both numbers. I'll be interested in seeing what the difference is like. Yeah.
How many different variables are involved in this premise? Wind speed?
Well, in all honesty, about a zillion. But if we ignore most of them, we can get it down to 2 or 3. Basically, is well, how how much light is reflected by the surface is going to depend on your angle from the nadir. That's just basically Fresnel's reflectance. But then, how much is really reflected depends on wind speed, because you don't have a level surface, so that's in there. And then, how much is reflected depends on your angle relative to the sun, because if you were looking this way, for example, you'd be looking right at the glint. If you were looking that direction, you'd be looking at your shadow. You don't want to do that. So something like 135 and 30 or 40 seems to be where there's the least variability in the fudge factor, so you can make the best guess, which is still maybe way off. And then, in all honesty, this reflectance also depends on what's the sky radiance, or the polarization of the sky, because how the light's reflected by the surface is polarization dependent. So clear sky, you know, sort of strongly linearly polarized at 135 from the sun, you get one answer. If there's a bunch of aerosols, that changes the polarization state. You really have a different factor. In the real world, you don't know what those numbers are. It's just kind of slightly educated guesswork. Yeah. And that's a real minus to measuring remote sensing reflectances from above water measurements, is you're always just guessing what the fudge factor is that you use to remove the surface reflectance.
We'll talk.
Of course, there's an equal number of uncertainties when you make measurements below the water and extrapolate up. It's the law of conservation of visitors.
So I'll do a little thing on shadowing at the end of this, but there was a big controversy for a while whether in-water techniques are better or above-water techniques are better. When you do this subtraction, the sky is actually very large relative to the water leaving radiance. And so making this correction is really, really important. So that sort of moved. My camp is more the in-water measurements to do this. The thing that really helps you, though, for the above water measurement is when you're doing it in turbid waters or with high absorption in the red, where the instruments, if you put it in water, is going to shadow tremendously. And so an above water technique definitely has advantages in high absorption places. But okay, so there's that. For the in-water techniques, to get the remote sensing reflectance, you measure the upwelling radiance at some depth. You have to transmit that through the air-water interface, which is this factor 0.543, which accounts for the reflectivity or the Fresnel transmission from the surface, and then the n-squared factor I told you about, divided by the downwelling sky irradiance times the transmission from thinking. This factor is basically to take the radiance you've measured at some depth and bring it up to the surface, so the transmission of the water. So you have to account for all these things to calculate RRS. The T of Z factor, as I say here, is you get from measuring a diffuse attenuation coefficient for the upwelling radiance, and Kurtzgood in his AOPs should tell you more about diffuse attenuation coefficients and how to calculate those. Okay, there's a new technique that we have for measuring above the water. So what we have now so far are the upwelling light from above the surface looking like this. And so you have to take into account the sky. The other method is measuring the upwelling light at some depth and taking that to the surface, transmitting it through the surface, so you get an LW plus in that technique. So that's the in-water technique. This technique that Jing-Pong Lee is pushing is basically you have a radiometer above the surface so that you're measuring the light coming up. So you don't have to do this transmission from here to there and the transmission through the air-sea interface. And to get rid of the glitter, he puts in some sort of a shield So there's no sky component onto that. So the light comes through, you have the upwelling light coming up to the surface, goes through the surface, and his detector is all up here in the air. So he's measuring LW plus without any kind of sky influence on the measurement. Okay, and this shield goes down into the water, so it has a nice surface that it's looking through. But he's trying anyway. That's one way to do it where you don't have to worry about this sky contribution, and you don't have to worry about these factors that transmit through the surface. And so during the radiometry lab, we actually have a setup to try to do this too.
So to what extent do you have to worry about shading of the instrument, particularly in turbid water?
Yep. Yep. No. This instrument will have a self-shading factor because it's shading this area underneath it. Okay, so yes, it has I would think it would have a big problem with shading in turbid water and places where there's a lot of absorption. You're right. That's my critique of this method. So.
What about the fact that the water surface is different? And obviously it's an effective time to remove, but you're saying the water is quiescent in it.
Quiescent, I'm not sure it necessarily would be quiescent. In the best cases, quiescent, it probably does get things going on in there, but you're right, the surface is not representative of the surface outside. That's another thing that's another thing I've not liked about this method. But it's a different method.
For setting up scenarios where you can do some modeling, where you can remove factors. I mean, in terms of representing what's actually going on in the world, it's not. But if you begin to remove surface effects, then you can actually look at other factors. Or do you think that it's actually not useful for that?
To do modeling of this and compare it to the other ones, are you saying, or?
Yeah. So to be able to do like some comparisons with Hydro Lake, where you're not actually really sure what the surface looks like. So if you're putting in your AC9 profile and you're running it through Hydrolite, and then you're comparing it to a measured radiance distribution or water leaving radiance, it's always going to be different because the way that you characterize the surface in Hydrolite, you might not even know what the surface is in real life. So you can guess. But if you could say, I've created a flat surface with no specular reflection, actually that's a pretty good way of measuring that.
My feeling, okay, so the last graph I showed the factor that you get for transmitting through the surface, all based on really good physics. If you start with IOPs here, do this measurement, measure the IOPs, try to get closure between the two. I think your uncertainties in the rest of the process are going to be way bigger than the transmission uncertainty that you get from the physics.
You could remove that from measurements and then begin to characterize what those uncertainties are.
Yeah, maybe. I don't. I can't. I don't know where there's a paper that I read. I don't know what I can say anything about it right now. That's sort of in.
If they agree between themselves, we have more confidence in the general approach. And the more they diverge, the more we understand we might have a major problem in one of them or so.
I don't know what. Okay, off the record, this method and that method seem to agree pretty well with a series of measurements that somebody did, and that's as far as I'm going to go on that right now. Next class, in 2 years, if you were in the class, I could discuss the paper that did that, but I can't right now. So, okay. What else? Oh, there's another factor, the normalized water leaving radiance that you'll see, and that's LWES that we've already seen, and then multiplied by the extraterrestrial solar radiance from a table, Nichols lab, or whatever, divided by r squared, where r is the Earth-Sun distance. So this is trying to normalize the water-leaving radiance by the RRS that you got before, and then multiplying back in how much irradiance would have been falling on that surface without an atmosphere and such. I think Kurt's going to talk a lot more about all these different normalized water-leaving radiances. So, okay, two other things that I was told I should mention in here, or we mentioned at different times in different classes and thought this would be a good place. There's this thing called the F over Q ratio. Okay, F is this factor that relates, easier to write it this way. F is a factor that relates the backscattering absorption ratio to the irradiance reflectance. Morel and others early in optical oceanography history measured the irradiance reflectance as the common factor that they would go out and, instead of measuring the upwelling radiance, instead of upwelling radiance divided by downwelling irradiance, they measured the upwelling irradiance divided by the downwelling irradiance. The reason was you could have one detector to do it. You would do a profile with an radiometer. You could flip that same detector over and do another profile. And so this thing would be independent of calibration errors to a certain extent, okay? And so they like to measure this irradiance reflectance. And you could use this sort of F factor relates the backscattering divided by absorption to this irradiance reflectance, okay? So that's an F factor that they did. F is on the order of 0.3 or so, a third, somewhere in there. It varies with all sorts of factors, solar zenith angle, and a lot of other factors, but it's about a third. Okay, so that's this F factor. Q, Q basically is equal to, was always defined as the downwelling or the upwelling irradiance divided by the upwelling radiance at nadir. Okay? The idea being that if you took EU, it'd be equal to Q times LU. If the upwelling radiance distribution was isotropic, then you would get this number Q would be equal to pi. Okay? So Q in reality in the ocean ranges from about 3 point, I've never seen it quite as low as pi, but say pi to 6, somewhere in that range, okay, depending on the wavelength. All right, so we have this formulation that looks like this. Morel, the idea is that if you look at the upwelling radiance distribution, you notice that it isn't flat, that it varies with angle. So if a satellite is measuring, one satellite is viewing the surface at this angle, and another satellite is viewing the surface at that angle, or you're making your measurements of light coming straight up, so you're measuring basically the surface, the light coming out at this angle, how do you relate all these things to each other? In particular, when we have multiple satellite missions, how do you relate what one thing sees at the surface to another thing at the surface? So Morel took this idea of Q and extended it to say you had Q, which is a function of solar zenith angle, and your two view directions. Okay. And then we have an F over Q factor. It turns out F depends on solar zenith angle, but I'm not going to put that in there. So this F over Q factor is a function of solar zenith angle, view direction, view nadir and azimuth relative to the sun. Okay, so we have this F over Q factor. And with this F over Q factor, the idea is it will offset or be able to correct for these different view directions of the surface. So that if I have one satellite measurement at some view direction, I can apply this F over Q factor and convert it to nadir, and I can compare the multiple satellite missions to each other. So that's a quick thing for F over Q. Why we bring it up here, I think Kurt's going to once again mention a whole bunch more about it. When we go out to make our measurements off the dock and in the field, you're going to do remote sensing reflectance. You're measuring the light that's gone up to the surface and going to your detector like this, versus the group measuring the in-water measurements will be measuring that angle. Okay, and so there's a reason why you would expect the two things to be different from each other. And this F over Q factor is trying to offset that difference. The Morel tables were all derived for case 1 waters, where the water properties depended, where it was easy to index the water properties by the chlorophyll concentration. And here's a whole bunch of references for you that will be in the slides stuff for the F over Q for Morel's corrections. They're commonly they're the only ones I know of being used in satellite missions right now. And when somebody asked about the radiance distribution, this is why we put a lot of effort into measuring the upwelling radiance distribution, is to validate these models back and forth. Yes, sir.
So F over Q depends on the IOP.
F over Q depends on the IOPs. It actually, there's a whole probably list of, yeah. So F over Q, okay, so let me put another one. Chlorophyll, if you're going to index, use this to get A and your phase function, okay? It also actually, if you want to be, it depends on the atmospheric properties, because it depends on the radiance distribution of the light coming down on the surface. And the wind speed. Although he puts the wind speed into a different factor. He tries to put the wind speed into that Gothic R.
Factor that corrects for the surface, which of course depends on the wind speed, but so does this guy.
Yeah, okay. And whether you're looking left or right, or
At this point, you've now done your duty.
okay.
Set them up for F over Q.
Okay, so there you are. So F over Q, yeah, it's such a fun thing. But anyway, that's one reason you measure the upwelling radiance distribution, is to be able to validate these, and that's why I ended up doing that stuff. In case 1, that works. Case 2, there's a couple papers that I just give you for a reference for how to do it. Pingley has a setup there. And shadowing. Mainly this is to get you some idea, but basically you put an instrument in the water, you're going to create a shadow from that instrument. Yet for satellite instruments, what we want to do is measure the upwelling radiance distribution, or upwelling radiance. And so we're trying to measure in that shadow to some effect, some extent. So either the instrument itself self-shadows, the dock, the ship, whatever it is you're standing creates a shadow. We're trying to measure the upwelling field, light field, so there's problems. There's a bunch of studies into this. The first thing, major results, avoid ship shadow. For a long time, we made measurements right off the side of the ship. You would take your radiometer on some sort of a I don't know, cage, put it on the side of the ship, lower it like you would a CTD, and maybe make at least an effort to have that on the sun side of the ship, but you know, sometimes it doesn't work well. So you do all these measurements in the ship shadow. So now we've gotten a lot better. We float away instruments away from the ship to try to avoid the shadow. But there were some studies showing how this effect occurs. And you want to be, in general, 10 meters or so away from the ship if you can, on the sun side to avoid the ship shadow. Instrument shadow to first order is proportional to the absorption coefficient times the radius of the instrument. So you can see that you want to use as small an instrument as you can to create as small a shadow as you can make. Gordon Ding did the calculations on this. But that you can remember, absorption of water increases tremendously in the red wavelengths. And so it can get in the red wavelengths where it's almost impossible to make a measurement without having instrument self-shadowing. Think about going out here in the Damariscotta River and how much CDOM you've got. Think about what size instrument you can get away with out there. And you'll see that it quickly becomes very hard to make an instrument that doesn't have shadowing of some sort. The best measurements I've seen for infrared or toward near infrared light is basically Dennis Clark took a ROV, and he has like a I don't know, 1.5 meter nose thing that sticks out and a fiber at the end, and this fiber brings the light back to a spectrometer on the ship and basically lowers this thing up and down. So the instrument collector is about so big, so it's not having much of a shadowing effect. So this gets fairly good data toward the 700 and 800 nanometers. But in general, you want as small an instrument as you can get. There's various calculations and correction schemes for this. Bob Leathers and Kurt and I can't remember her first name, Mallory Downs, had a correction for the TSRB, which is tethered surface radiometer buoy. And so they describe the correction in that paper. Giuseppe Zabordi had a correction scheme for larger structures. Giuseppe is involved with these above water measurements. Anyway, so he does it for like the docks and structures that his detectors are on. I'm involved with MOBI, which you'll find out about in the future. Jim Muller has at least a first generation shadowing correction. I'm supposed to have a telcon about a second generation to try to do corrections for MOBI. The important thing with all these is, at least at this point, none of these have a Raman, which, you know, you're trying to do the correction. It's really important in the red wavelengths, but that's also where Raman's important. So it's sort of bad that way. Jim's got a correction that includes Raman that we work on. So keep shadowing in mind is the big deal. Okay. I'm sorry, it's taking me a long time.